All right. Well, hello, everyone. We're going to officially begin our seventh unit. Remember, we discussed in a small preview last time we were together. This is a unit on systems and more. But we are going to today uh, just focus on systems, systems that I like to call more like a mega system, just because, well, they have more variables. And so we want to be able to solve for X, Y, and Z. Later, we'll throw some more variables in there. But what you're going to find out is that when you have a system like the one here, x plus y minus z equals 8, 2y plus z equals -1, and 2x plus 3y equals 11. When you have a system that has more variables, you're still, you might say that your goal is to try to combine and cancel equations so that you can still produce two variable equations. You see, if we can turn this into two variables, then we know what to do, just like you showed in class last time. So let's see if we can do some combining and canceling and end up with two variables. Now, when I look at this problem, there are honestly a couple things that I see. It doesn't really matter what order you see them in, but you can't miss that the bottom equation already contains two variables. And notice that those two variables are x and y. So maybe I can combine the top two equations so that I can end up with just x and y. And it looks like that I can do that because something else that is hard to go unnoticed is that the z's in those top two equations are already opposites. And so the problem is a little bit easier because we can just add these two equations right from the start. We can cancel the z's, and maybe even more importantly, we can end up with another equation that has just x and y. So let's add down, and when I add those equations, the x, nothing adds or cancels to it, so I still have x, but my y and 2y will give me a 3y, and then again, the z's cancel out. Now, one of the mistakes that I'll see sometimes in these problems is that people will forget to add the constants. Those are 8 and -1, which they will add to be 7. Now, do you see what happened here? We combined the top two equations so that we could end up with another equation made up of x and y. And that's kind of my little scratch off here. The guy's, the little thinker guy, is saying, by the way, when you add your equations together, you want to make sure that it's going to end up being the same two variables that you produce. What I mean by that is if I'm going to add equations together, I want to add them together so that I get the same variable to cancel or the same variables to be produced. And in this problem, it was the x and y that was being produced because obviously the z was canceling. So I've got the same variables. And I know you're probably saying, yes, Mr. Nair, let's get on with this. And so let's do that. Let's now treat this sort of this blue system as now my system that I'm trying to solve. And yeah, those three y's, they could be opposites if I just multiplied through by a negative. And so I'm going to say that that's probably the best thing to do because if you add those together, you get the y's to cancel out, and you also end up with just x equaling 4. Remember that once you get your first answer, you want to plug that back in, not to the top equations, but plug it back into your smaller system. I'm just going to squeeze it back in here for this x. I'm not going to think of it as a negative x. I'm going to think of it as its original x. So I plug a 4 in there. I still have a 3y. It still equals 7. Remember, I didn't think of it with the negative signs. And now I get y equals 1. Only after I have both of my x and y, only after I have two of my variables, do I decide to go back up to the top equations and solve for z. And, you could plug into any one of those top equations that contain a z. Noticing that the second equation is kind of easy because all it has is a y and a z. So I'm going to plug y equals 1 back into that second equation. And when you do that, you pretty much end up with your answer, because, wait a minute, yeah, you plug a 1 in there for z, for y, so I'll plug a 1 in there, but I still have a plus z, and that is supposed to equal -1. So of course that means z equals -3. Um, System solved. But we do want to write the answer as a point. X equals 4, y equals 1, and z equals -3. Yeah, that actually is a point. It's actually a three-dimensional point, because you would graph it on the x, y, and z axes. Since our point came out to have x, y, and z, what that really means is that we were finding the intersection of three planes. Now, the intersection of three planes ends up being a point, or you might say it could end up being a point. In the case of the problem that we just solved, it was. Interestingly, though, three planes can do all kinds of things. They may not intersect at one point that would be right in the middle. It may be that they intersect at three lines. It may be that they intersect at two lines. It may be that they intersect at one line, or maybe they don't intersect at all. Now, don't worry, we're not going to be spending too much time with this, but I did want to show you that when you're talking about X, Y, and Z, you're actually talking about planes, and planes can intersect in a variety of ways. If they do intersect, though, as a point, that would be like this last scenario. That means that our system is consistent and independent, and most of the systems we solve are going to be that way. Let's solve another one. Let's solve for x, y, and z. Now, none of these equations, after you jot them down, none of these equations have two variables. So we're going to have to work some magic here. We're going to have to cancel a variable, so that we can end up with two variables. Now, again, there's all kinds of things that people see. Sometimes people are drawn to these two x's because, of course, they're almost opposites. That is, if one of them was a negative, they would be opposites. I'm going to actually kind of start the problem by focusing on the bottom two equations, and I'm going to multiply through by a negative. Just switch the sign on everything. Now, everybody knows that the x's are going to cancel, but notice what I'm going to be left with. I'm going to be left with y and z, specifically -3y and -z. Don't forget to add the constants, because that'll leave you with the number 1. Now, I've got a y and a z equation. I need another one. Now, what I can do is I can add any other combination of equations besides, obviously, the second and third. So maybe I decide to add the first and second equations. Maybe I decide to add the first and third. I can add any combination I want, as long as it's not the one I already did, as long as it's not equation 2 and 3. So what do you want to do? Do you want to add the first equation with the second equation? If you do, then that means that you're going to need to make the x's cancel again, so that you can end up with y and z. So I'm going to add the first and second. I guess that's the decision that we made. That means I need some opposites. So multiplying by -2 is the best way to make those x's become opposites. Now, you can organize this any way you want. I mean, some people would rewrite the problem altogether. I'm going to just kind of write my new version up above, honestly, a little bit to save some space here. Everything is being multiplied by -2. Just a little by the way, make sure that your z's look like z's and your 2's look like 2's. I can't tell you how many times I've gone to look at a student's work. They asked me to try to help them find their mistake, and basically they misread a 2 as a z, or vice versa. So how did I do here? Everything's multiplied by -2. Now I'm going to add my new first equation with my existing second equation. Okay, the x's cancel out. The y's are going to add to be 3y. The z's, negative 8z's. And negative 24 and 5, I'm pretty sure that's negative 19. Now, once you have canceled the same variable twice, now I have two variable equation made up of y and z. And again, it's system time. It's time to solve that system like you've solved many. It looks like the y's are already opposite, so I can add and cancel those. The z's are going to be negative 9s. Negative 9z's equaling negative 18, so I'm pretty sure that means z equals 2. Now, remember, once you find your first answer, I can't think of a time that you wouldn't want to do this. You plug it back into your smaller system. And so when I plug back in, I'm going to choose to plug in here just because I kind of see a nice little minus z there. So we plug in the number 2. Now it's, of course, going to give me a minus 2. So 3y and a minus 2 equals 1. I'm pretty sure that means that y equals negative 1. Yeah, y equals negative 1. And now that I have my z and my y, I can take both of those and I can plug it back into my original system. Of course, I can plug it back into any one that I want. How do you feel today? Do you want to plug into the second equation? It's kind of looking a little lonely there. So we'll plug into the second equation for y and for z. Let me see if I can get this right. It's going to be 2x minus y. So that's 2x minus an already negative 1. And what else was in that equation? A minus 2z. So minus 2, remember z equals 2. And what does this equal? This one equals 5. But yeah, the point here is that you plug back in to the original equation once you have your first two variables. Looks like we get some plus plus business here. I'm pretty sure that this plus 1 and this minus 4 is going to become a minus 3. And that means x equals 4. Okay, we have another nice consistent system. X equals 4, y equals negative 1, and z equals 2. We're writing the answer as a point. And don't forget that that point should check in all three equations. If you have a little extra time, you can do that. Now, had we been in class, what I would have done is put this next system up on the board and said, try it. And that's what you guys would have done. You would have tried it. You would have seen if you could solve it. So I'm going to ask you to do that right now. Push pause on the video and try it. Can you solve this? It's kind of an interesting problem, isn't it? Every equation has two variables. So what's your favorite two variables? Do you like x's and z's, like the first equation? Then you're going to want to add the second two equations, but you're going to want to make the y cancel. Maybe you like x and y. Maybe you like x and y. So you're going to have to add the first and third equations, but you're going to make which variable cancel? Z. And did you get the idea? You could do the third equation if you want. Maybe you like y's and z's. So that means you're going to have to make the x's cancel in the first two. But push pause and see if you can solve this system, and I'll meet you back here in a moment with the method that I would have used. All right, the method I would have used would have been to make an x and z equation. The reason for that is because I noticed that in the second and third equation that the y's are almost ready to cancel out. They're basically almost opposites, and they will be opposites if I just multiply through by a negative. Now, be careful here. because the 5x does not add to anything, even though it's lined up with the y. The y's do cancel out. And then that 4z, same thing. It doesn't add to anything. Now the 4's that are constants, they both add to be 8. So now I have my original first equation, 2x plus 2z. That's matching up nicely with my new equation that I got from doing a little canceling. And so we're kind of back to a basic system where maybe you can multiply by a -2 so that you can make those z's cancel. Just be careful that you maybe temporarily kind of ignore that equation so that you can add the first and now new equation. What's happening here? Are we getting x equals 4? It looks like we are. If you plug 4 back in for x, maybe you plug it back into the top equation, then I'm pretty sure I'm going to get 20 out of that. And 4z equaling 8. I think if you subtract and solve that, you're going to end up with z equaling 3. Is that right? No, -3. Good catch there. And was your y value a decimal or fraction? It should be. But interesting, if I go back to my original equations, you know, I don't actually need x and z to be able to solve for y. I really just need x. It says 5x plus 3y equals 4. So that means 5 times 4 plus 3y equals 4. So yeah, this is going to end up being 3y equaling -16. So it's all right to get a decimal. Doesn't mean you're wrong. You can write it as 5 1/3. You could write it as what? 16 thirds, -16 thirds. So yeah, it looks like x equals 4. It looks like y equals -16 thirds, and z equals -3. How did you do with solving that one? If you solved it with a different method, of course, you still should get the same answers. And it's homework time. Now, with your homework, there's a couple more standard systems, but you're going to want to really focus your time on the mega systems that are kind of the second half of the homework. Work on them like you normally would. You do not need to upload them. You do not need to upload them tonight. You can just have them prepared in class tomorrow for a possible homework check. And at that time, we'll continue working through Unit 7. All right. Have a great day.